Lesson 63, the importance of mass. We will discuss why mass is crucial to understand Newton's third law. This is something that I usually always talk about because it's actually the second, in my opinion, Newton's third law is a bit complicated because it's got two tipping points. The first tipping point is the fact that it involves two forces, but the second tipping point is the fact that it sort of links to mass. Now, a full understanding of Newton's third law doesn't really matter whether you understand it or not, but a lot of students still get this a little bit confused, so I like to go through it anyway. Real quick look at what we did last time. Last time I had you guys, what we did was we looked at Newton's second and third law. We did Newton's first law, which is like an object in motion will stay in motion, and then when an object at rest will stay at rest. So therefore, when this train stops, that person is still in motion, so it will keep that motion forward. This is called the law of inertia, and it's the tendency for an object to keep its current velocity. These plates and bowls, they're going to keep their current velocity, which is 0, not moving. So even when you pull out the tablecloth, they just don't move. Then I set you guys on to work on 10.3. Newton's second and third law. Newton's second law is stated by force equals mass times acceleration. So when you do give something an unbalanced force, if you do apply an unbalanced force, it'll accelerate. So that means it'll change its velocity. It'll speed up, or it'll slow down, or it'll change direction. That's the kind of things that a force can do to an object to accelerate it. And the amount that it accelerates it, the amount that it speeds it up, or the amount that it slows it down, or the amount that it changes its direction is dependent on the mass. The heavier the object, the lower the acceleration will be. So then what we did was we looked at some examples, and then we did some, I still haven't added this yet, but we did some graphs and some free body diagrams. And then what we did is we talked about falling through the air. This was a quick little thing that I finished up on. All things fall through the air at the same acceleration. They all fall down at 9.8 meters per second squared. They will all fall at that same acceleration, increasing that speed at the same rate. The only reason why we don't see feathers falling down the same speed as bowling balls is because there's an extra force acting on it to make the net force, and that's air resistance. And that will lower the force, which then of course lowers the net force, which of course lowers the acceleration. In a vacuum, they fall at the same speed. And then we talked about Newton's third law. Newton's third law is whenever one object exerts a force on the second object, the second exerts the same force, or every action has an equal and opposite reaction. If you push against the wall, a wall will push back on you, and it will push back on you the same amount in the opposite direction. We did some examples, and then we sort of started to run out of time. So we looked at how to tell so because we said there are two forces, an action and reaction, you can actually start to pair them up. But it's important to be careful. An action-reaction pairs must be the same size, act in opposite directions, but act on different objects. The example that I always give where students get this wrong is I go a table, I draw an apple on it, and I say, well, this apple experiences, that's the worst apple I've ever drawn. This apple experiences two forces, one downwards by gravity, one upwards by the normal force. And these happen to be the same size, tick, they happen to be in the opposite direction, tick, but they are not on different objects. So therefore, we say that these are not action-reaction pairs, even though they look like action-reaction pairs, because they need to be on different objects. If a car crashes into a bus, it's not just the bus that it's not just the car that feels the force, the bus feels the force too. Both of the objects get damaged. Now, what is the importance of mass in this whole story? Well, the importance of mass in this whole story can be simplified, and we're going to tackle it when we deal with this bus. I'm actually going to do a quick little side break before I do that, but before I do that, the bus and the car will experience the same force, but they'll experience the force differently. The bus probably won't get very damaged, but the little car will probably be crushed. So why, if they experience the same force, if they both are affected by the same force, why do they experience it differently? And that is the importance of mass. it's pretty much the end of the lesson. So I could pretty much just wrap the lesson up now. Yep, done, guys. Cool. But let's explore it a bit more. Before I do that, I wanted to do this question. I kind of wanted to come back to this question because there are a couple of, and this is the question I wanted to come back to. There are a couple of times whenever I do a question, sometimes I make mistakes and I get really self-conscious and I'm like, crap, and then I want to fix them. And so I wanted to actually fix this one because I felt like I did a really crappy job of explaining it. And it actually took me, honest to God, I had to remember how to solve these types of questions. Elevator questions for me were always really challenging because I always used to get them wrong because I used to draw the wrong force vectors. The thing with me that always made elevator questions really good, and this is what I always strongly suggest you do, and it's one of the only things you can do in physics, is to try to relate this to your everyday life. If you're in an elevator and it starts moving down, what do you feel? I know when an elevator starts moving down quickly, I start to feel a bit like I'm on a roller coaster. I start to feel a bit lighter, like I'm floating. So that means my force of gravity might not be as strong. And so therefore that gives me an idea of how I should approach the question. Whereas when the elevator is going up, I usually feel a bit squashed. And so it's like, okay, so I should use that to help understand it. And once I applied that to this question, I got it right. The reason I got this question also really wrong is because I missed out on one of the words. So let's look at this. A physics teacher decides for fun to stand on some bathroom scales calibrated in newtons in a lift. Scales provide a measure of the force which push up on the teacher. That's the part that I missed out on. When the lift is stationary, the reading of the bathroom scale is 700 newtons. So what we could do, and this is what we did last time, force equals mass times acceleration. We've got 700 newtons. We've got mass times 9.8. We can use that to get that the mass of the teacher, 700 divided by 9.8 is about 71 kilograms. By the way, if you're still trying to pay at home, 700 newtons, that's only got one significant figure. So really, we should just write 70 kilograms. But we're not going to because, again, I sometimes ignore that fact when I do questions because I'm just like, if I just write 70, that's probably not what the answer in the back of the book is. Let's get our elevator going here. So here's an elevator. Here is our teacher in the elevator standing on some scales. What forces are involved? We've got a force downwards, which is the person pushing down on the scales, and we've got a normal force upwards, which is the scales pushing up on the person. Those two are that's an action-reaction pair, and so therefore that's why it's 700, 700. For the first one, there is no net force. Even if the elevator moves upwards at a constant speed, there is no net force because there's no acceleration. If there's no net force, there's no acceleration. The answer to A is 700 newtons. Did someone ask a question? Nope, no one asked a question. Cool. 700 newtons. What will the reading on the scales be? So that's what it's going to say initially because there's no acceleration. So the elevator goes up. So then what happens for B when it starts to accelerate downwards? And so I made a mistake on this one initially, but I got it correct the second time. So now the elevator drops, right? The elevator goes down suddenly. It accelerates downwards 2 meters per second squared. That means that there is a downwards force, right? I actually calculated this. I went, okay, well, the downwards force is going to be the mass times the acceleration. We already know the mass because we just did that. We did the mass was 71 kilograms. So if we go, well, the force is going to be 71 times 2 because for mass times acceleration, the acceleration is 2 meters per second. That's how we get 142 newtons. So the net force downwards has to be 142 newtons. So that means if the net force downwards has to be 142 newtons, the only way to make sure that this works is to change the force upwards, because obviously the person's still going to push down on the scales of 700 newtons. It's not really going to matter that it's not going to really matter that the person, like, it's still pushing down because it's still experienced gravity of 700 newtons. We haven't changed gravity, but now there has to be, the net force has to be 142 newtons down because it has to go downwards. So therefore, the only way to do that is to change this normal force to be 558 newtons. I'm not sure if technically these are now action-reaction pairs. I would assume not, because now I actually didn't think about this problem when I was looking at it, because now these values are different. I'm not sure how that would work, but that's in general what you would see on the scale, because you feel, and that's why you feel lighter. The floor doesn't push up as much on you when you're going down in an elevator. And that's how we measure whether we feel heavy or not. The more we get pushed, the more that normal force pushes up on us, the heavier we feel. If you drop someone off out of a plane and they start falling towards the ground, there is nothing pushing them upwards. So therefore, they don't really feel heavy at all. You just feel like you're floating. And when you're in an elevator, you sort of feel like you're floating. That's why it's 558. As for, is this an action-reaction pair? I don't know. I think there's probably something more complicated going on here with the normal force. It might be that there's a force upwards as well, which counteracts the gravitational force. But this is generally how I would do the type of question. I'm going to have to do more research on this question, which is annoying because I thought that I was done. The last part is the upwards force. So the upwards force, when you're accelerating upwards, now what happens is that you've got a force upwards of 142 newtons. And that's because, again, F equals ma. We've got in this case 2, and we've got 71. So therefore, 142 newtons is the force upwards. And so therefore, in order to balance that force, we need to counteract that. So we need to push upwards with 842 newtons. That's the force that the elevator is pushing up on the person, essentially, because it's pushing up through the floor. I think the reason why, actually, I think that's the answer. I think the reason why these aren't action-reaction pairs is because this force here, this upwards force, includes the normal force plus the force of the elevator. So the elevator is pushing up with 142 newtons, but then it's also including the normal force, which is 700 newtons, which is why it measures 142. Great, cool, 842. Great, we don't need to do more research. I just wanted to go through that because, as you can tell, it confuses me as a teacher, so I imagine it might confuse you guys. But the trick that I'll always apply is this. I could easily figure out 142 newtons. The question was, am I subtracting it or adding it? If I'm going up, I feel heavier, so the normal force must be more, so I should add it. When I'm going down, I should subtract it. So that hopefully helps you out. It may confuse you guys more, and if it has confused you more, good. More good. What type of teacher is happy with their students confused? If this confuses you more, that means there are still some things you need to learn. That means that you have the potential to get a better understanding of the physics going on here. And that means you might need to do more research. Maybe my explanation wasn't very good. Maybe you need to have a one-on-one chat with me at lunch. Maybe instead you need to jump onto YouTube and see a physics YouTuber explain how this works. How does forces work in an elevator? You might get lucky. You might find a YouTuber that actually does this experiment. You could do this experiment. There are no elevators on campus, which is a bit unfortunate, like no elevators at school. But you know, maybe someone's already done a video on it, so it could be worth watching. I might even see if I can find one for you and put it online. So that's the elevator problem. What I thought I would finish up on, we'll talk about now, is this problem with mass. What time have I got? It's 11:35. I've got about 15 minutes. I've got a couple of slides to go through. But a lot of them are examples, so we don't need to worry too much about them, but we'll definitely start to talk about them. I wanted to approach this question. So this is the importance of mass and why do different objects experience it. So here's, if for every action there is an equal and opposite reaction. All right, cool. Why does the skateboard move forward? If, in this example, and I always use this one, if the bat and the ball both experience the same size force, so they both experience the same size force, but they act in different directions. This is an action-reaction pair. The action-reaction pair in this case is the ball being pushed this way and the bat being pushed this way. With the skateboard, there is the force that the foot pushes backwards on the ground, and the force that the opposite force pushes the skateboard the other direction forward. The question I always stumped me, and I actually really think that this is important to understand, is if these are the same size forces, shouldn't the bat fly backwards, you know, with the same speed? These are the same size forces. Shouldn't the ball fly forwards at the same? Shouldn't the ball fly to the left at the same speed, and they should just fly apart? Every time you kick a soccer ball, if the soccer ball goes flying forwards, then surely you should go flying backwards. But that's not the case, and that's because of mass. I'm just going to grab my charger. Just give me a second, because you might have just seen my laptop just said you're running low on charge. 1 second. So let's move away from this conundrum then. Why does everything not fly away like this? If I hit the golf ball with a club, why does the club not go as far as the golf ball? They both experience the same force, and that's because they experience the force differently. Let me explain what I mean by that. So when two objects interact with one another, there is an equal force, but the force is experienced by both objects. The objects accelerate differently depending on their mass. I guess because you guys are in VC, I should also add and other forces. So let's just talk about what that means. So when you've got an astronaut sitting above the Earth, they feel the pull of the Earth because they've got a gravitational attraction. And the Earth is going to get pulled up by the same amount of gravity, the same gravitational force. But if you then go, well, if that's a gravitational force, F of G, then the astronaut's acceleration is going to be, A equals F divided by M. Now for the astronaut, his mass, that could be a pretty large value. But for the Earth, you can't see that because it's a bad color. But if I look for the Earth, A equals F divided by M. This is actually not an accident, guys. I've done a massive M. That Earth is huge. The Earth is gigatons worth of mass. And so therefore, that mass is such a large number that the force is going to be, the acceleration is going to be pretty much zero. I say pretty much zero, but yeah, it's going to be pretty much zero. If not, it's going to be like 1 times 10 to like the negative 5 newtons or something really meters per second squared. It's going to be a really small number. And that's just not going to accelerate. It's just not going to move because it's so massive. So even though they both experience the same force, and if you ever see a question that says which one experiences more force, they both experience the same force. But the Earth, because it's so massive, experiences that force differently. It experiences it as a very, very, very small acceleration, whereas the person will experience it as a very, very large acceleration. Let's compare that to the bat and the ball. The ball, its acceleration is going to be, it's got a very, very small mass. So therefore, it's going to experience a very high acceleration, where the bat is got a larger mass. So therefore, it's not going to experience as much acceleration. The other part about this as well is that technically the bat, you're holding the bat. And if you're holding the bat, then that means that if you're holding the bat, then you've also got mass. And so that's also going to need to get moved by the same force. You're also attached to the Earth because you're standing on the Earth. And so if the bat pushes you this way, the Earth is going to push back with the same amount. So as long as you're holding the bat correctly, the bat probably won't move that much. If you were standing on roller skates, you might move backwards a little bit, but not very much compared to how much the ball moves. Let's just say both of them experience, let's put some numbers in. I love putting numbers in because it sometimes helps. Let's just say they both experience 100 newtons worth of force. The ball is probably 0.1 kilograms. So if we go 100 divided by 0.1, that's going to give us 1,000 meters per second squared, which is a bit insane, but whatever. It's not really accurate. You wouldn't be able to hit it with 100 newtons worth of force, but whatever. Whereas you are going to experience 100 newtons worth of force, but if we take your mass plus the bat's mass, let's say it's 80 kilograms. In contrast, you're only going to experience like a very small amount. So 100 divided by 80, you're only going to experience, 100 divided by 80. You're only going to experience 1.25 meters per second squared. 100 newtons is a bit too large of a number, but whatever, it doesn't matter. 1.25 is a lot smaller than 1,000. So you are really not going to move very much, but that ball is going to go flying. The bat itself might move a little bit more, but yeah, again, remember, it has to move your body as well in order to fly back at the same force. So that's why this is why mass is so important, because it helps us know how an object will experience that force. Is this related? Let me check. Not really. We'll come back to this. This is the classic example. I'll read this out to you guys, and I'll you know, I'll ask the question in chat, and I want you guys to give me the answer. We haven't got too much time left, so I'm just going to push through this last little bit here. I might save this one for when we talk about Newton's. I might talk about this briefly now, just so that I can cover it. When you walk, because a lot of people get this bit confused, you push down and backwards on the ground, and that's actually a force of friction. You push down and backwards, and because of that, the ground pushes up and to the right. And what that means is that you will experience a force in this direction here. But when you break that force down into an up force and a right force using this angle here, you can then figure out how much forward you push. And you guys know that if you push backwards a lot, you might move forwards, but if you push down more, then you actually can sort of jump in the air. If you want to jump in the air, you push straight down. You don't push down and backwards, because that'll make you jump forwards. I just found this picture and I thought it was really useful. And I used to get confused sometimes when I came to how do the forces work with walking. We're going to do a lot more of this breaking down forces into component forces in the next part of the chapter in 10.6, I think, or chapter 11. But we're getting up to that, so don't stress yourself. Don't worry about it too much at the moment. We've got one example that we're going to talk about, and then that's, did I do the rowing example? Do I do the rowing or the bus? Let's do the bus, because the bus is a clear example. While driving down the road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus and the bus hits the firefly. Which of the two forces is greater? All right, guys, I want you to answer this question in chat. Don't disappoint me. Which force is greater? The force of the firefly, the force on the firefly, or the force on the bus? Which force is greater? Which one of these two do you guys think? And come on, I want you guys to get the answer correct. All right, answers: the force on the firefly is greater than the force on the bus. Okay, come on, what do the rest of you guys think? Come on, I want to see whether or not you understand what we've just been talking about. Which force is greater? Firefly. The force on the firefly. We've got 3 people saying firefly, 4 people saying firefly. Which force is greater? Got a firefly hitting a bus. The bus hits the firefly. Which one experiences the greater force? I want to see a couple more answers. I'm looking at Phoenix, I'm looking at Kang, I'm looking at Lucius. Well, I'm not actually looking at them, but I want them to give me some answers. I'm looking at Daniel, I'm looking at Imran. I wonder if Imran's on today. Is Imran on today? He usually gets Imran. Tam, why do you don't have to message privately. I'm gonna push you out. Tam says they both experience equal force. Okay, and what about Yvonne? What do you think? What about Vince? What do you think? What about Tien? Which one experiences more force? Come on, guys. If you just make a guess. The firefly from Rochun. Yep, cool. Firefly from Tien. Okay, here we go, ladies and gents. This is, of course, as you guys hopefully would have, I was hoping you guys would figure out, ladies and gents, this is a trick question. Okay, Newton's first law. They both experience the same force. And I was hoping that I would get a bunch of people coming in and saying, "Oh yes, sir, isn't it the same force?" But no. Instead, I had every single person saying firefly. The firefly does experience a greater acceleration. Why? Because even though they both experience the same force, the acceleration by the bus they both experience the same force, the acceleration by the bus is going to be a lot smaller than the acceleration by the firefly. And that's because the bus is so massive. So yeah, it's a trick question. A lot of you guys fell for that mistake, and a lot of you guys straight away showed me that you don't fully understand Newton's third law. They both experience the same force. Even though that fly is very, 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 very small, it still experiences the same force, okay? And that's something that's important for you guys to take away and to think about it. Even though they might experience different accelerations, they experience the same force. Ladies and gents, that brings us to the end of this lesson.